So thanks to Sagar and the nice introduction, and we have talked a lot about the fundamental of power amplifiers, mostly in the standalone PA, from the very basic ones for the first speaker and to the most advanced waveform engineering and the simulation tools introduced by Sagar and Diamond. And I'm going to share our latest research on the more perspective on the load modulation power amplifier, especially on the load modulated balanced amplifier. And I will show how this can be more advantageous for the emerging wireless communications. And so this is the outline of my talk. I'll start with the introduction. Then I will briefly talk about how we can revisit the load-modulated balanced amplifier theory, or LMBA theory, and how we can configure various modes with this unified platform. Then I'm going to introduce the practical design methodologies for this LMBA and some of the design examples. Then the next session will be focused on how we can achieve the linear LMBA and the load mismatch insensitivity with this circuitry. And I will end with a conclusion. So as we know, power amplifier, we have been talking about a lot in today's session, and it is an essential component in the wireless communication because for any wireless link, according to the channel theorem, we need a sufficient amount of power in order to achieve this capacity, designated channel capacity. And the power amplifier is the key unit to provide that high enough power for the antenna radiation. And it is also a converter that converts the DC energy to the RF energy, so its efficiency is critical. And as you can see, the power amplifier is the most power-hungry unit in all the wireless platforms, and it can consume up to 50% of your battery power in the smartphones. And in the base station, it is almost equal to the combination of the CPU, GPU, baseband, and transceiver, plus the touch screen. So it is really a lot of power being consumed by this single unit of power amplifier in your smartphones. And in the base stations, this power consumption ratio is even more. It could be up to 80% in the total power consumption. So we definitely need to achieve a highest possible efficiency for the power amplifier. But as you can see from this figure, as we're evolving in the wireless communications, so the x-axis is the data rate from 2G all the way to 5G and plus. And we can see that the typical PA efficiency drops dramatically from 50–60% in the 2G all the way down to only 10% or even below in the latest standard. And the root cause for this is the modulation. So that the modulation here you can see in the left figure is that the essence of wireless communication is that we need to encode all the wireless data onto the radio wave, especially in its amplitude and phase. So that means the amplitude of the radio wave is constantly varying. And this variation can be qualified as this peak to average power ratio, or PAPR. And intuitively, the higher data rate we want to achieve, the higher the fluctuation of this amplitude is. So as we can see in the 3G, we have the PAPR typically around 4 dB, but it has been increased to more than 10 dB in 5G due to the much higher data rate and much more complex modulation. But from the power amplifier perspective, if we examine this typical class B PA, it can only achieve the peak efficiency when at the peak of its envelope, where the DC level matches the AC level, as you can see here around this region. But when the power fluctuates down, the DC level maintains while the AC level drops, so that the efficiency you can see keeps degrading as the power backs off. So representing the peak as the average ratio. So in order to achieve this highest possible efficiency for transmitting this modulated high PAPR signal, we definitely need to improve the efficiency after power backoff, such that we can minimize this energy dissipation indicated by this red region. That's the overhead between the DC and AC. So this is the reason why the load modulation has been a very important and effective method to achieving the high efficiency for transmitting this modulated signal. And the typical implementation is the well-known Doherty PA. So this is its circuit configuration. So Doherty PA consists of a main and auxiliary amplifier being connected with this combiner network, which is combined two quarter wave transmission lines. So with this network, we can divide the operation in two regions. So when the power is low, that this peak amplifier is turned off and only the main amplifier is operating, because the main amplifier is biased in class AB mode, while the peak amplifier is biased in class C. So this, with the peaking device being turned off, this main amplifier sees a high impedance load impedance, twice of Z0, ideally, so that it can saturate earlier in the lower power, creates this is effectively by shifting the class B PA efficiency curve towards the left-hand side, toward the low power region. Well, when the power reaches this peak at the lower backoff, the first efficiency peak, then the peaking device starts to turn on, and those two active devices, they are load modulating each other through this combiner network in those two equations. And what happens to the efficiency is that we can maintain this high efficiency towards the full saturation of those two amplifiers altogether. And then in the full saturation, the main and auxiliary amplifiers will generate the same amount of power or current, so that their load impedances are being equalized and close to Z0, or the RLOPT in the PA design. So with the Doherty PA, as you can see, we can achieve a very nicely enhanced efficiency curve, such that we can achieve much higher efficiency when transmitting this modulated signal. So this is why we need load modulation. And then we can see that there are more challenges for the next generation power amplifier beyond this efficiency. The second challenge is the wide bandwidth. So as you can see, our wireless communication bands are keeping proliferating. So we currently have 50 plus bands globally within the 5G FR1 range. And you can see in the iPhone phone board, to cover all of those bands, we need a lot of those radio front-end modules. But if we only have narrowband PAs, you can see that we need a large number of those power amplifiers in order to cover the entire bandwidth FR1 range. So this is not sustainable in space due to the limited area in the phone board. And also the space is also limited in the base station, because we're currently evolving from the single antenna to the large antenna array, known as the massive MIMO. So the space is always being limited. So it is much more convenient to have wideband PAs, such that one PA can cover a large spectrum range, so that we can minimize the number of amplifiers within this limited to cover the entire range within the limited area of the space. Of course, the ultimate solution would be to just have one amplifier to cover the entire spectrum, and this would be the ultimate solution. So besides the efficiency and bandwidth of the power amplifiers, there's another new challenge for the next GPA that is known as the load impedance mismatch. So since we're evolving from the single antenna to a large array, in the array operation, each PA is not only transmitting the signal through this antenna, but the antenna is also receiving signal from the adjacent antenna element. And this received signal is functionally equivalent to a reflected wave to the amplifier, or a load impedance mismatch, as indicated by this equation. And this impedance mismatch or fluctuation is highly dependent on the beam scanning angle and the location of this antenna array. As you can see, when the beam is scanned in the azimuth and elevation angles, the variation of the load impedance of the antenna varies in the very different way in comparison between the center unit and the edge element in this array. So at the system level, this antenna impedance mismatch can lead to the main beam distortion when all the PAs are being connected to this antenna array. So this figure shows this is captured from one paper published by Professor Christian Figger's group in 2017. It shows the EVM of the main beam versus different elevation and azimuth scanning angles. As we can see, only within very limited range in the blue color, we can achieve the low EVM such that it allows the transmission of high data rate 1024 quad signal. But for the majority of the scanning range in the red color, due to the high EVM, we have to downgrade to the low order of modulation, let's say the 16 quad. So the purpose of massive MIMO is to enhance the spectrum efficiency by allowing, but due to the main beam distortion, we have to downgrade the modulation and decrease the spectrum efficiency so that we must make the PAs more resilient to this load mismatch and resolve this main beam distortion such that this main massive MIMO can really work. So in summary, for the next generation power amplifier, we need to keep pushing the technology boundaries at different levels in terms of the device, circuit architectures, and system levels such that it can meet the ever increasing requirements in terms of the efficiency, linearity, bandwidth, the carrier frequency, the output power, and most emergently, this array friendliness such that it can tolerate the antenna impedance fluctuation in the array. So then I'm going to introduce the new LMBA and the theory and how it can really achieve those challenges, address those challenges. So I'll start with treating this 90 degree hybrid coupler and show how it can make a good load modulation combiner. So as we can see, the most classical load modulation platform is this Doherty PA, and this is its combining network. What we originally discovered in this paper is that we can basically replace the Doherty combiner with this quadrature coupler, this very classical platform component, and by connecting the main and auxiliary amplifier to this through and the coupler port of this quadrature coupler, will short circuit this isolation port, and it can achieve an exactly equivalent function as the ideal Doherty combiner. What's more is that we recently have this new parallel Doherty configuration, and again, it can also be realized with this quadrature coupler, but we need to exchange this main and auxiliary amplifiers and open circuit this isolation port. So as you can see, this quadrature coupler can serve as a universal combiner to realize different Doherty modes, and also it can be used to realize this LMBA mode, where we can introduce a control amplifier to supply a control signal to this isolation port so that the balanced amplifiers can be load modulated equivalently. So, and this creates the LMBA configuration, which I will introduce in detail in the later slide. So as you can see, this quadrature coupler 90 degree can be used to realize different load modulation mode within a unified circuitry. So this nice feature enables reconfiguration of this RF circuits in different modes based on different application scenarios. So this offers a lot of design flexibilities and operational flexibilities. and multi-mode and multi-standard operations. Okay, so conventionally, the LMBA theory is derived in impedance domain by treating this quadrature coupler with this Z matrix. But I will first time show that it can be revisited with the signal flow chart. So here we can see that this, if we only have the input signal from the BA input, what we can see here, due to the directionality of this quadrature coupler, both BAs sees only a forward traveling wave. And in microwave world, this means a constant load impedance. Well, when there is a control signal travels from the other side, it provides this reflected wave in the reverse direction, and this can lead to a variation of the load depending on the magnitude and phase of this control signal. And then with that, we can rederive the load modulation theory of this LMB and the equations. So when, for example, for this control signal, JIC, theta, we can, after it is being fed into this quadrature coupler, it can be quadrature split with those two signals. Here, I'm assuming a branch line coupler. And then what we can see here, due to the orthogonality of this current sources of those three amplifiers, this control signal can be fully returned, fully reflected, bounced back. So here in this balanced amplifier port, we actually have three currents: the incident current IB and this control signal and its reflection. So in order to calculate the load modulation of this balanced amplifier, its load is equivalent to the total voltage divided by the current it's generating. And the total voltage is going to be contributed by all those three currents, the IB, IC forward, and IC reflected. So this is the total voltage expression over the current is generating. And here it leads to the famous, this classical LMBA design equation that we derived previously by using the Z matrix. And then we can see that from the control amplifier's perspective, due to the directionality of this quadrature coupler, it sees no reflection, so that its impedance is always constantly equal to Z0. And then I will show how we can effectively operate this LMBA platform by combining it with the Doherty type of biasing. So we can basically set the Doherty type of biasing in two modes, Doherty-like modes and the pseudo-Doherty modes. For this Doherty-like modes, here we set the balance amplifier as the carrier and this peaking amplifier or the control amplifier as the peaking. So the carrier in class A and peaking in class C. So in this case, only the carrier is being load modulated by this equation. As we can see, when the load modulation starts with the IC being turned on, then we need basically the impedance of this carrier needs to be decreasing such that it can generate the higher power during the load modulation. So in this case, we basically need to set this control phase to be ideally 180 degrees such that we can make this sign to be negative to make sure that the load is modulated to the lower impedance region during the turning on of the peaking device. Well, for this, this is the Doherty-like LMBA. For the pseudo-Doherty LMBA, its configuration is reversed, where we are setting this control amplifier as the carrier and the balanced amplifier as the peaking. So here again, the carrier amplifier sees a constant load, while the peaking amplifier only is being load modulated with this equation. So since we need to modulate the load to a lower impedance level when the peaking current is turned on, so the peaking current becomes this IB in the denominator, so that here, the ideal condition for the pseudo-Doherty LMBA is that we need to set the theta to be 0 degree, such that when the peaking device is turned on, then it will modulate the impedance to a lower value of region. Okay, so those are the two Doherty-like and pseudo-Doherty modes of LMBA that we can possibly operate this platform. And then the next question is, do we really have to enforce the balance of those two quadrature-coupled amplifiers? And the answer is not really. So if we set the balanced amplifier B1, B2 with two individual current still in quadrature phase, and we found that we can rederive this load modulation equations for all three amplifiers individually. And ideally, all three amplifiers can be load modulated individually with properly selection of this current amplitude. And with this set of equations, basically all the load modulation modes are being formulated, no matter it's Doherty or LMBA. And here, basically, the BA1 and BA2, they are not equal to each other. So this means that they are asymmetrical. So we renamed this mode to be asymmetrical LMBA theory. So it is a more universal load modulation platform and theorem. And then with this asymmetrical LMBA theory, we can further form high-order load modulation modes with this 90-degree quadrature coupler. So first, the high-order load modulation mode is derived from this Doherty-like LMBA, where the balanced amplifier is set as the carrier and this control amplifier is the setting. So here, the balanced amplifier can be set with the one as the carrier and another one as the peaking. So basically, here we have two peaking amplifiers. One is the BA1 and the second is the control amplifier. So, and they can be turned on at different power backoff levels. So first, at the lower backoff, we only allow the operation of the turning on of the BA1 so that you can see with the control amplifier being turned off, those BA1, BA2, they basically creates a ideal Doherty, parallel Doherty PA. So with this design equation. So then once they reach the saturation in the middle of this backoff range, we then turn on this peaking device. So at this range, those two carrier and the BA1, they are being both saturated and rebalanced so that after the turning on of the secondary peaking device, the second load modulation range is exactly equivalent to this LMBA with this design equation. So here we have the Doherty region and LMBA region for operating this amplifier such that we can achieve this multiple efficient peaks along this dynamic range. And in this case, the set of the control phase of the peaking device needs to be set as 180 degree. Another high-order load modulation modes can derive from this pseudo-Doherty LMBA or PD-LMBA, and where we set the control amplifier as the carrier and the BA1, BA2 as the primary and secondary peaking. And similarly, the operation can be divided to two regions, the Doherty region with the carrier and the first peaking, and the ALMB region with the secondary peaking being turned on. And I'm going to introduce this mode in detail in later slide. And as you can see, it can achieve this high-order load modulation modes with extended power backoff range. So in the next section, I'm going to introduce the practical design methodology for this LMBA and a few design examples and prototypes. So first, the most advantage of the LMBA over the conventional Doherty is that it is not limited by the quarter wave lines, that is the bandwidth limiter. And also it can extend the dynamic range from the 60 dB of the conventional Doherty to more than 10 dB of this LMBA. So the asymmetrical Doherty also has the similar issue of the bandwidth and the degradation between the two efficiency peaks. So here I'm going to introduce the details of the pseudo-Doherty LMBA. So as you can see, by setting this control amplifier as the carrier in class AP and the balance amplifier as the peaking in class C, we can achieve this enhanced efficiency curve and with extended power backup range and improved efficiency over the entire dynamic range. And also it can be nearly very broadband with the proper design of the phase alignment between those two amplifiers. So here's the detailed operation of this PD-LMBA. In the low power region, this peaking device is turned off and only the carrier is operating, so that it, just like Doherty, it can achieve a high, the first efficiency peak and the lower power backoff. And then as this target backoff power, this peaking device starts to turn on, and then it can be load modulated until reaching the saturation. So the design of this PD-LMBA requires the proper amplitude and phase control. And we'll start with amplitude control. So for the first efficiency peak has to be designed as the designated power backoff, for example, 10 dB in this case. So this basically sets the ratio between the power of the carrier and the peaking device, roughly equals to 10 dB. If the peak, because the peaking device will generate the majority of the power in the saturation region. And the second, we need to synchronize the turning on of this peaking device and the saturation of this control amplifier or the carrier. And this can be realized by setting different turning on threshold of this peaking device and properly choosing the power dividing ratio of this as the input power divider. So both this gate biasing voltage of this peaking device and the power dividing ratio as the input are effective to set this synchronize the turning on of this CA saturation and the BA turn on. This is the amplitude control, and then we need to properly control the phase such that it can achieve the optimal load modulation behavior. And the more tricky case is how we can align the phase to make sure that this load modulation is properly achieved in this realistic circuit. And in the conventional Doherty PA, this is the major challenge because the PAs as the current generation sources, they're not directly connected to the output to the load modulation combiner, but there are output matching and the parasitics in between. But for the LMBA, I assume this is not a problem. So here we can see that the BA current and the BA input signal comes from the left-hand side, and it will travel across this input coupler and hits into those two amplifier devices with both the input and output matching networks as well as the parasitics. And then the carrier, the control signal comes from the other side. And we just need to make sure that when those two waves, they meet at this intrinsic drain plane of the devices, they must be in phase or 0-degree phase shift such that we can achieve this optimal load modulation condition for this PD-LMBA operation. So in this case, the question is how we can achieve this condition. And this can be transferred to the phase delay of those two signal paths. So as we can see, from the signal travels from left to right in the BA path, it passes through 3 building blocks. the coupler, input coupler, the input match network of BA, and the BA device itself. But for the signal travels from the other side, in the CA side, the signal passes through more building blocks, the input-output matching and the device of the CA, the output quadrature coupler, and the output match network of the BA. So it travels across more building blocks. So in order to equalize the phase and achieve this 0 degree of phase offset between those two signal paths, all we need to do is to add an extra phase offset as the input of the BA with complementary phase response, so that those two signal paths has equalized the phase delay. And in this case, those two input signals can be fully in phase, and they can be supplied with a standard Wilkinson divider from a single RF source. So this is how we can make the RF input. So this means that as long as we're able to make this good phase alignment, we can make this LMBA intrinsically broadband. And eventually the C and B output are going to be in phase combined as the RF output. And then also it can enable the use of complex output match network. And this gives us more design flexibility in the design such that we can apply this more complex high efficiency mode like the inverse class F, the class E, such that we can further enhance the efficiency at the device level. So here I'm going to show how much bandwidth, how broadband in this design, this LMBA could be. So here I'm introducing our latest IMS paper, which is going to be presented in this year's IMS about 1 month away. So here we're demonstrating a ultra broadband LMBA that can achieve the decade bandwidth from 0.2 gigahertz all the way to 2 gigahertz. And this is the circuit board with this. Here we are using this ultra broadband quadrature coupler supplied from a commercial vendor. And here is the overall design with the input splitter, the phase offset, and the BNCA. So here we can see that the phase offset between the BNCA can be set very close to 0 degree along the entire frequency range from 0.2 to 2 gigahertz. And with this alignment being enforced, we can see that the load modulation behavior can be almost maintained very close to the real axis across this entire frequency range. So then here is the measurement results. We can see that the very nicely achieved efficiency enhancement behavior from peak power to 10 dB power backoff has been achieved all the way from 0.2 to 2 gigahertz, covering this decade bandwidth. So this is the first ever decade bandwidth, 10 to 1 bandwidth load modulation period that has been ever demonstrated, and it can nearly achieve frequency agnostic. And then I'm going to make an overall comparison with the LMBA with the state of the art. So here I'm marking this all those LMBA prototypes we developed in the recent years and map them into this comparison graph. Here the peak power is marked as this rectangle, as this triangle in this figure, and the efficiency, average efficiency across band at this 10 dB backoff is marked as the circle. And then, as you can see, a high efficiency can be achieved for both the peak and at the lower backoff can be achieved and maintained almost when the bandwidth extended to unlimited range for this LMBA. So with all those prototypes we developed in the recent years, and it compares very nicely with the state of art. As you can see, that the efficiency keeps drooping as the bandwidth increases. So this really means that with LMBA, we can overcome the conventional performance bandwidth trade-off, and that we can really push the technology boundary with this new PA architecture. So in the next section, I'm going to further introduce how we can make LMBA linear and make it load mismatch insensitive. So to make a linear LMBA, I'm going to introduce another, the high order load modulation mode derived from the PD-LMBA. And here we're setting this control amplifier as the carrier, and the BA1 as the primary peaking, and the BA2 as the secondary peaking. So it creates a imbalance between those two balanced amplifiers. And it creates a hybrid load modulation behavior. So we renamed it as the hybrid asymmetrical LMBA or HA-LMBA. So overall, it can achieve more enhanced efficiency with two efficiency peaks in this power backoff. So in comparison with the PD-LMBA, it can further enhance the backoff efficiency as indicated by this red curve. And here's the detailed operation. Again, the low power region is the same as the PD-LMBA, where the carrier operates standalone with the constant, and it sees a constant load impedance for this control amplifier. And when it reaches to this low power backoff, then this primary peaking device BA1 is turned on. And then those two amplifiers, they are load modulating each other like a Doherty mode, so that both the load impedance is modulated towards the lower impedance direction for both the carrier and the peaking devices. Then once the power reaches this high power backoff, then the secondary peaking device is turned on such that the BA1, BA2, they are continued to be load modulated towards the lower impedance region, but the carrier amplifier's load modulation is reversed in this region. And in this region also we can see that this BA1 and BA2, since BA2 is turned on later, so they are always being asymmetrical to each other. So this region is called the A-LMBA region. So in this region, the power generation is dominated by those two peaking amplifiers. So even though this there is a reverse of the load modulation of the carrier device, then it does not affect the power generation. So here we can, with this HA-LMBA, we can achieve this nice three-way load modulation behavior. And then we further discovered that by properly optimize the biasing at this phase offset, we can further linearize this AM-AM and AM-PM of this overall performance. Basically, we need to turn on the primary and secondary devices slightly earlier to avoid the saturation, so that we can make this AM-AM more flat. And also, this AM-PM behavior can be linearized by offsetting this input phase delay between the B and C. But in comparison with this efficiency optimized design of this phase offset, we can see that for the linearity optimized design over the entire frequency range, it must be retuned. So here I'm showing an example of the design from 1.8 to 3 gigahertz. As you can see, we need different delay length of this phase offset for different range of these frequencies. So here we need to adjust this phase offset to linearize this AM-PM of this HA-LMBA at different frequencies. But this is achievable with this realistic designs. We can always tune the phase like a phase shifter. Also, what we further discovered is that this HA-LMBA can be made load mismatch insensitive or resilient to load mismatch. All we need to do is through the bias reconfiguration. first reconfiguration is that we can probably set the DC supply voltage of the control amplifier. And then we can also exchange the turning on sequence of the secondary and the primary peaking of BA1, BA2 for different loading and for different region of load mismatch in the Smith chart. And with all of this, so here you can see overall, the bias tuning has to be done with this VDD of the C and VGS and of BA1, BA2. So with all three bias voltages being reconfigured, as we can see, when the load is mismatched, for example, to 2-to-1 VSWR, we can maintain almost a consistent efficiency enhancement behavior, like very close to the response at the match load, as well as this linearized AM/AM and AM/PM, very close to this match load in this baseline curve. So here I'm not going to show the detailed theory of this load and mismatch resilient operation. For the details, you can check our latest paper for how we can achieve this behavior in theory. And then this prototype is being designed and fabricated, and here we're measuring it with this setup to evaluate its behavior, its performance at both the matched and mismatched load. And here, this different phase offset line is being realized with the trimmable phase shifter. So basically, we add different patch to this phase shifter so that we can tune this this length of this delay line such that the AM/PM linearization can be always achieved at different frequencies. So here I'm first showing the measurement results at the match load. Here, as you can see, for 3 different frequencies, we can achieve the nice efficient enhancement behavior together with the linearized AM/AM and AM/PM. And also for the modulated measurement in this right-hand side figures, we can see for 1.8 and 2.6 gigahertz, we can achieve both very low EVM, close to 3%, and also the high average efficiency up to beyond 50% for those 2 different frequencies. And then I'm going to show how this LMBA can be reconfigured to offer good resilience to the mismatch. So here we can see that when the first is the modulated measurement, the constellation diagram being measured at the match load, where this 256 QAM, we can achieve the EVM of 3.5%. But when the load is being mismatched, you can see the EVM is largely being corrupted, mismatched to 0.5 Z0, for example. And then we demonstrated that with the optimal reconfiguration of the bias voltages, the VDD, CA, BA1, and BA2 gate biasing were able to recover the EVM of the transmission under this load mismatch. And in this reconfiguration, we do not need any extra tuning element, but just to tune the bias voltages of those 3 amplifiers. And this can lead to minimize the complexity in the real-world implementation. And then here I'm showing the modulated measurement at this entire 2-to-1 VSWR mismatch at 2.6 gigahertz. As you can see, when the load is mismatched to 2-to-1 VSWR, this average efficiency can be maintained very close to the matched condition, beyond 50%. And also the EVM, more importantly, is that the EVM can be effectively recovered from this red curve that is being that is the results performance without any bias tuning, and through the mismatch resilient tuning, we can recover the EVM almost equal to this matched condition. So this shows the very effective that this LMBA can be operated at the end operation in the phased array, in the array operations. So in conclusion, here I'm introduced that the quarter coupler can really form a variety of two-way and three-way load modulation modes as a unified load modulation platform. And then to combine LMBA with Doherty and with this new design methodology we introduced, it can achieve unprecedented efficiency, power backoff range, and especially the bandwidth almost unlimited. And then high linearity can also be achieved with the proper configuration of the LMBA, which can also be made very resilient to the load mismatch VSWR with the bias reconfiguration. And also it offers promising prospects of scaling to the microwave applications for in the silicon technology. And finally, I would like to acknowledge my group for their hard work. And also those are the work my group has been demonstrated winning over the past 5 years, including one of this best paper award in IMS with our first ever demonstration of the PD-LMBA. And also I'd like to acknowledge our sponsors for supporting this work. Okay, thank you.